Hi, I'm John Wolpert. I'm the Seeker of Awesomeness for Consensus Labs here in Washington, D.C. Consensus is a company that operates in many countries. We're the largest blockchain company right now in the world by many accounts, and one of the fastest growing software companies in the world, and by many accounts the largest blockchain company in the world. We help businesses start up on the new Internet of Transactions, on the blockchain, and in particular on Ethereum. So I'm here in DC with the team looking for new ventures to get behind, to help bootstrap and to get going faster. We're a new venture development lab. So my experience of the evolution of blockchain, which I think is pretty common, was a number of years ago hearing about Bitcoin and cryptocurrency and thinking that was novel and interesting. But I was at IBM at the time working on the Watson team. And that was artificial intelligence and pretty interesting unto itself, so I didn't pay it a lot of attention. Then a few years later, my boss, one of my favorite people at IBM, who's now the head of IBM Blockchain, Jerry Cuomo, called me up and he said, "Hey Louis, it's Clark." And I said, "Well, what do you want, Jerry?" And he said, "Well, there's this thing called blockchain. I mean, we don't know a lot about it, but there's gold in those hills. Go out and find it." And I said, "Well, give me a ship and crew and I'll go investigate." And he said, "Well, I got a canoe, 2 dogs, and a musket." And I said, "Well, okay." And we got lucky. It turned out that blockchain was we got halfway across the Mississippi and looked over our shoulders and found that there was a wagon train behind us, and now we're running a boom town. And there was definitely there was a there. So we got lucky, and that's how I stumbled into blockchain. Every use case I've seen in industry to date since 2015 that tried to do something with blockchain, that said, "Hey, let's do this on blockchain," has every single one of them has proven why it doesn't need blockchain. And everyone that says, "Hey, let me look at this problem differently through the lens of immutability, of decentralization, of a number of nuanced ideas that are actually packed up into primarily public blockchain technology, especially around token economics and what you can do with this emergent notion of being able to not just gamify human interaction. Gamification is just keeping track of scores, but then turning that into an economic set of decisions, right? I'm going to vote, or I'm going to bet that this fact is true. Well, if the consensus is that it's false, I just lost not just a point, but real economic value in some way, either in money, real money, or some kind of other value, maybe voting points or something else. So it's applying this notion of powerful public blockchain is effectively a high precision instrument for seeing problems differently and then instrumenting them in ways that would have been way too expensive and difficult to do if we had the old rails only, right? We needed a new railway to run these kinds of transactions, one that's more nimble, one that's more precocious, more always available. And once you have that kind of new rails, you have an infrastructure that can allow you to just do things completely differently.
Welcome to the first course in the blockchain specialization titled Blockchain Basics. Let's start by asking ourselves, what is a blockchain? Why should you care about it? Unlike traditional methods, blockchain enables peer-to-peer transfer of digital assets without any intermediaries. It was a technology originally created to support the famous cryptocurrency Bitcoin. The blockchain by itself has taken a life of its own and permeated a broad range of applications across many industries, including finance, healthcare, government, manufacturing, and distribution. The blockchain is poised to innovate and transform a wide range of applications, including goods transfer, for example, supply chain, digital media transfer, for example, sale of art, remote services delivery, example, travel and tourism, platform for decentralized business logic, for example, moving computing to data sources, and distributed intelligence, example, education and credentialing. Additional applications of blockchain include distributed resources, for example, power generation and distribution, crowdfunding, for example, startup fundraising, crowd operation, for example, electronic voting, identity management, for example, one ID for all your life's functions, and government public records and open governing. Moreover, blockchain can enable an inclusive economy. It can enable a person in a remote corner of the world to partake in a democratic process. Opportunities for innovative applications are endless. There is a dire need for critical thinkers, designers, and developers who can envision and create newer application models on blockchain to benefit the world. This course is a first step in addressing this need. At the end of this course, you will be able to explain the three fundamental characteristics that define the blockchain using Bitcoin blockchain. Bitcoin is not the only player in town. By the end of the first module, we'll move beyond Bitcoin into introducing the next generation blockchains with Ethereum. You will also be able to discuss the important features of Ethereum blockchain that is used as a reference implementation in many newer blockchains, and explain the algorithms and techniques that enable the blockchain, including a public key cryptography and hashing. Finally, you will be able to outline methods for realizing trust in a blockchain. Let's begin with an introduction of Bitcoin. Two major contributions of cryptocurrency Bitcoin are a continuously working digital currency system and a model for autonomous decentralized application technology called the blockchain. Though our focus is on a general blockchain, we have to understand the working of the technology behind Bitcoin to fully appreciate the innovation of blockchain. We can all agree that the advent of the internet and the World Wide Web has transformed every aspect of our lives, from stock markets to street corner food trucks. It has enabled the technology explosion with Web 2.0 and the world of e-commerce applications. Around 2008-2009, when the institutions and markets we trusted were crumbling down and everybody was running away from the Wall Street, a mysterious person or persons called Satoshi Nakamoto introduced a new digital currency, a cryptocurrency called Bitcoin. Bitcoin enabled an innovative platform for peer-to-peer transfer of value without any central authority. With no central authority, how did Bitcoin realize trust and security? By implementing software programs for validation, verification, consensus in a novel infrastructure called the blockchain. Later on, in about 2012-2013, computational elements were added to the blockchain infrastructure that has opened up a whole world of possibilities beyond simple currency transfer. These innovations are significantly shaping the direction of Web 3.0, as you will learn in the next 4 courses. What is a blockchain? Blockchain is about enabling peer-to-peer transaction in a decentralized network, establishing trust among unknown peers, recording the transaction in an immutable distributed ledger. Let's understand centralized versus decentralized network using a common scenario. Consider a scenario where a customer wants to buy an item using her credit card. Let's enumerate the intermediaries involved in accomplishing this task. We have a credit card agency, we have a customer bank, we have a credit cards bank, we have an exchange, we have the merchant's bank, and finally the merchant. This is an example of a centralized system that we are so used to. Now compare this with a system where peers can transact directly with each other, irrespective of where they are located. Functions of the intermediaries are shifted to the periphery, to the peer participant in the blockchain infrastructure. Peers are not necessarily known to each other. This is a decentralized system. How do we establish trust among the peers in such a decentralized system? By having a process in place to validate, verify, and confirm transactions. record the transaction in a distributed ledger of blocks, create a tamper-proof record of blocks, chain of blocks, and implement a consensus protocol for agreement on the block to be added to the chain. So, validation, verification, consensus, and immutable recording lead to the trust and security of the blockchain. Now I'll explain these concepts using another scenario. I'm lending Amy $10,000. This is one single peer-to-peer transaction. We both make a note of it on a ledger. What if I change my entry from 10,000 to 11,000? Alternatively, Amy changes hers from 10,000 to 1,000. To prevent this trust violation, we need to seek the help of people around us, Lisa, Allison, and Francis. Provide all of them a valid copy of this ledger. This is the basic concept of an immutable distributed ledger defined in a blockchain process. In this scenario, we were all physically present in one location, Amherst. Now imagine this to be an online transaction to an unknown peer. Also, scale up the one transaction to 10,000 transactions. How about 1,000,000 transactions? I should be able to transact with equal ease to any unknown peer in Amherst, Albany, or Albania. Maybe to send some flowers to a friend in Albania. This is the tenet of a decentralized system supported by blockchain. In the case just described, how do we trust our unknown peers? Through verification and validation. In our example, Amy requests Kevin to verify the amount I transacted with her. Kevin checks it. Oops. Kevin finds the amount of transaction is not 10,000, but 300. Not valid. Kevin rejects and nullifies the transaction. Similar to this, validation and verification methods defined by the blockchain and implemented by the peers provide the collective trust needed in a decentralized system. Summarizing, blockchain technology supports methods for a decentralized peer-to-peer system, a collective trust model, and a distributed immutable ledger of records of transactions. Here is the basic structure of a blockchain. Transaction is the basic element of the Bitcoin blockchain. Transactions are validated and broadcast. Many transactions form a block. Many blocks form a chain through a digital data link. Blocks go through a consensus process to select the next block that will be added to the chain. Chosen block is verified and added to the current chain. Validation and consensus process are carried out by special peer nodes called miners. These are powerful computers executing software defined by the blockchain protocol. Let's now discuss the details of a single transaction. In Bitcoin, a fundamental concept of a Bitcoin network is an unspent transaction output, also known as UTXO. The set of all UTXOs in a Bitcoin network collectively define the state of the Bitcoin blockchain. UTXOs are referenced as inputs in a transaction. UTXOs are also outputs generated by a transaction. All of the UTXOs in a system are stored by the participant nodes in a database. Now let's review the role of the UTXOs in a Bitcoin blockchain. The transaction uses the amount specified by one or more UTXOs and transfers it to one or more newly created output UTXOs, according to the request initiated by the sender. The structure of a given UTXO is very simple. It includes a unique identifier of the transaction that created this UTXO, an index or the position of the UTXO in the transaction's output list, a value or the amount it is good for, and an optional script, the condition under which the output can be spent. The transaction itself includes a reference number of the current transaction, references to one or more input UTXOs, references to one or more output UTXOs newly generated by the current transaction, and the total input amount and output amount. Participants can validate the transaction contents. Does the UTXO's reference the input exist in the network state? This is the only one of the many validation criteria. Recall our demonstrated scenario. This is similar to Amy asking Kevin to verify the money in the envelope to be $10,000. Are these UTXOs valid? All right, it is time to explore a real transaction. It is available at this link. At the top left is the transaction number. Just below, there are 3 input UTXOs referenced, and an arrow points to the references of the 2 output UTXOs. Note that there are 3 input UTXOs and only 2 output UTXOs. This means that the total amount in 3 input UTXOs are spent to generate 2 new output UTXOs. Just below the output UTXOs is a total amount transferred in the Bitcoin value. That is shown in green. Let's now move on to learn about a block. As you can see, a block is composed of a header of information about the block and a set of valid transactions. At first, we'll examine the Genesis block. It's available at this link. We introduce this block number 0 for posterity's sake. This is where it all began. Satoshi Nakamoto initiated the Bitcoin blockchain with one transaction of 50 Bitcoins or 50 BTC. This one transaction created a UTXO output for Hal Finney's address. The date of the blockchain creation is January 3rd, 2009. There was no previous block. This field is all zeros. It also lists a block reward or miners fees of 50 BTC. We'll discuss miners reward in a later lesson. Let's now look at the more recent block 482808. On the right panel, note the current block hash. The previous block hash, that is a link to the previous block, and on the left panel, down here, the nonce. You will learn about the block hash computation in the module quiz and in the later lessons. Now let's look at the structure of the blockchain by peeking into the Bitcoin blockchain. Our goal is to understand the link between the blocks. Let's consider the chain of 3 blocks: 488867, 488868, 488869. 488868, shown in the middle, has the hash of 488867 as its previous hash. Block 488869 has the hash of 488868 as its previous hash, forming the links in the chain. To summarize, transactions bring about transfer of value in the Bitcoin blockchain. The concept of UTXO defines the inputs and outputs of such a transaction. Once a block is verified and algorithmically agreed upon by the miners, it is added to the chain of blocks, namely the blockchain. Now that we have reviewed the basics of a blockchain and its basic structure and origin, let's consider the basic operations in a blockchain. Operations in the decentralized network are the responsibility of the peer participants and their respective computational nodes, for example, laptop, desktop, and server racks. These operations include validation of transactions, gathering the transactions for a block, broadcasting the valid transaction in the block, and consensus on the next block creation, and chaining the blocks to form an immutable record. In this lesson, we explore some of the fundamental operations of the Bitcoin blockchain. First, we have to discuss the participants. There are 2 major roles for the participants. Participants that initiate transfer of value by creating a transaction, additional participants called miners who take on added work or computation to verify transactions, broadcast transaction, compete to claim the right to create a block, work on reaching consensus by validating the block, broadcasting the newly created block, and confirming transactions. You might wonder why participants would take on additional work. Well, The miners are incentivized with bitcoins for their efforts in managing the blockchain, as we'll find out. Transaction validation is carried out independently by all miners. The process involves validation of more than 20 criteria, including size, syntax, etc. Some of these criteria are referenced input unspent transaction output UTXOs are valid. Recall, UTXOs were defined earlier in lesson 2. Reference output UTXOs are correct. Reference input amount and output amount match sufficiently. Invalid transactions are rejected and will not be broadcast. All the valid transactions are added to a pool of transactions. Miners select a set of transactions from this pool to create a block. This creates a challenge. If every miner adds the block to the chain, there will be many branches to the chain, resulting in inconsistent states. Recall that blockchain is a single, consistent, linked chain of blocks. We need a system to overcome this challenge. The solution? Miners compete to solving a puzzle to determine who will earn the right to create the next block. In the case of Bitcoin blockchain, this puzzle is a computational puzzle and is central processing unit or CPU intensive. Once a miner solves the puzzle, the announcement is broadcast to the network and the block is also broadcast to the network. Then other participants verify the new block. Participants reach a consensus to add a new block to the chain. This new block is added to their local copy of the blockchain. Thus, a new set of transactions are recorded and confirmed. The algorithm for consensus is called proof of work protocol, since it involves work or computational power to solve the puzzle and to claim the right to form the next block. Transaction 0, index 0 of the confirmed block, is created by the miner of the block. It has a special UTXO and does not have any input UTXO. It is called the coin-based transaction that generates the miner's fees for the block creation. Currently, the miner's fees is 12.5 BTC for Bitcoin. This is how new coin is minted in Bitcoin. To summarize, the main operations in a blockchain are transaction validation and block creation with the consensus of the participants. Yet, there are many underlying implicit operations as well in the Bitcoin blockchain. Let's now look beyond Bitcoin. Bitcoin blockchain is open source and the entire code is available on the GitHub. During the initial years beginning roughly in 2009, this open source code was extended to release different cryptocurrencies. About 300 plus cryptocurrencies were introduced. Bitcoin supports an optional and special feature called scripts for conditional transfer of values. Ethereum blockchain extended this scripting feature into a full-blown code execution framework called smart contract. A smart contract provides the very powerful capability of code execution for embedding business logic on the blockchain. Based on such capabilities, 3 major types of blockchains emerge from Bitcoin Foundation. Type 1 deals with the coins and cryptocurrency currency chain, example Bitcoin. Type 2 supports cryptocurrency and a business logic layer supported by code execution, example Ethereum. Type 3 involves no currency but supports software execution for business logic, example the Linux Foundation's Hyperledger. With the addition of code execution comes the serious consideration about public access to the blockchain. Hence the classification of public, private, and permission blockchain based on access limits. We have been watching Bitcoin blockchain continuously operational since its inception, all supported by its public participants. Thus, Bitcoin is a fantastic example of a public blockchain class. Anybody can join and leave as they wish. Transaction blocks in the blockchain are publicly observable, even though participants are anonymous. It is open source. You can also create new coin digital currency by modifying the Bitcoin code. Wallet applications provide the basic interface to transfer value through the Bitcoin blockchain. In a private blockchain, access to the blockchain is limited to selected participants. For example, those participants within an organization. This restriction helps in simplifying the normal operations such as block creation and consensus model. The third classification of blockchain is permission blockchain, also called consortium blockchain. It is meant for a consortium of collaborating parties to transact on a blockchain for ease of governance, provenance, and accountability. For example, a consortium of all automobile companies or healthcare organizations. Permission blockchain has the benefits of a public blockchain, with allowing only users with permission to collaborate and transact. In summary, significant innovations such as smart contracts have opened up broader applications for blockchain technology. Private and permission blockchain allow for controlled access to the blockchain, enabling many diverse business models. Bitcoin blockchain is the mother of all blockchains. It was intended for peer-to-peer transfer of value, and it does that well. Around 2013, a framework for code execution was introduced by Ethereum founders. The centerpiece and thrust of this Ethereum blockchain is the smart contract. Consider this tag diagram comparing Bitcoin and Ethereum blockchain. On the left is the Bitcoin blockchain and a wallet application for initiating transactions. On the right is Ethereum that took a significant step towards transforming the blockchain into a computational framework that opened up a whole world of opportunities in the decentralized realm. Ethereum supports smart contracts and a virtual machine on which smart contracts execute. Smart contracts in turn enable decentralized applications that accomplish more than a transfer of value, efficient automation of decentralized applications such as supply chain. Smart contract is an important topic that we have allocated a full course for this topic in this specialization. In this module of Course 1, we'll provide a high-level overview of smart contract as it relates to Ethereum. After completing this module on Ethereum, you will be able to discuss at a high level the innovation of the Ethereum blockchain, namely the smart contract, illustrate Ethereum blockchain protocol, structural elements and operational aspects, demonstrate the concept of gas, the fuel or the payment model for code execution, and the incentive model for the Ethereum blockchain. What is a smart contract? Let's review the basics. A smart contract is a piece of code deployed in the blockchain node. Execution of a smart contract is initiated by a message embedded in a transaction. Digital currency transfer requires simple addition and subtraction. Ethereum enables transactions that may carry out more sophisticated operations. For example, a transaction could require a conditional transfer. It may require some evaluation. It may need more than one signature for transfer of assets, or it may involve waiting for a specific time or day. Let's consider an example of what a smart contract can do. An auction bidding smart contract could execute this logic. If the age of a bidder is greater than 18 and the bid is greater than the minimum bid, then accept the bid, or else reject the bid. This can be done by a smart contract. What does a smart contract look like? How do you write a smart contract? Structurally, a smart contract resembles a class definition in an object-oriented design. It has data, functions or methods with modifiers, public or private, along with getter and setter functions. Specific programming languages have been designed for coding smart contracts. Solidity is one such language. Let's examine a simple Solidity smart contract to understand its structure. First line with pragma indicates the version of the Solidity language. The contract's name is in the first line. This particular contract is for one integer storage. The data for the integer is defined with type and name. uint stored data. Two functions are defined for writing and reading the data, set and get. Code execution. Where does the code in the smart contract get executed? Where is it located in a node? We need a computational infrastructure to execute any arbitrary code. Every node in Ethereum network should be able to execute the code irrespective of their underlying type of hardware or operating system. Enter Ethereum Virtual Machine, EVM. An EVM provides a run anywhere abstraction layer for the contract code. A smart contract written in a high-level programming language is translated into EVM bytecode and then deployed on the Ethereum Virtual Machine, EVM. Every node will host the same smart contract codes on their EVM. Summarizing, smart contracts add a layer of logic and computation to the trust infrastructure supported by the blockchain. Smart contracts allow for execution of code, enhancing the basic value transfer capability of the Bitcoin blockchain. The code for the smart contract is written in a high-level language like Solidity and compiled into bytecode. The code for the smart contracts is executed on a special structure known as Ethereum Virtual Machine.
Ethereum has worked out marvelously on how to solve these problems of scaling and privacy and a number of other issues that needed to be worked out for public networks. You have the Enterprise Ethereum Alliance that is the largest organization of entities working on the Ethereum protocol and maturing it into something that industry can use. But at the same time, companies around the Hyperledger project, the Fabric and Roha and Sawtooth and all these other protocol initiatives under the Linux Foundation and what they call the Hyperledger project, that has led to a whole bunch of other breakthroughs around channels and contract segregation. So you might remember I was saying you and I have an agreement. And we need to all be in control, but not anyone having the control of the system. All right, well, that's fine. But if you and I have a confidential agreement, and nearly all business-to-business agreements are confidential. It says right on the contract, it says, not only is this contract confidential between you and me, the existence of it is confidential. Most of the pharmaceutical industry operates on this, and the medical industry operate on this principle for good and bad. You could say, well, we'd like some more transparency there, but we also don't want your medical records out in the clear, and we don't want the price that you're paying for, the fact that you're even paying for a particular drug to be out in the clear, right? Or that you're using a particular drug, right? That's not okay. So we need transparency for some things and opacity for other things, and getting that mix right is really hard, right? So we need things like channels and sharding, and now in Ethereum, Plasma, and what we call layer 2 technologies that are coming out this year and next that really will transform our concept of blockchain.
Bitcoin blockchain state was defined in terms of unspent transaction outputs, UTXOs, and a reference implementation of the wallet application that held the account reference. Ethereum formally introduced the concept of an account as a part of the protocol. The account is the originator and the target of a transaction. A transaction directly updates the account balances as opposed to maintaining the state, such as in the Bitcoin UTXOs. It allows for transfer of value and messages and data between the accounts that may result in the state transitions. These transfers are implemented using transactions. There are two types of accounts: externally owned accounts and contract accounts. Externally owned accounts, are EOA, are controlled by private keys. Contract accounts, or CA, are controlled by the code and can be activated only by an EOA. An externally owned account is needed to participate in the Ethereum network. It interacts with the blockchain using transactions. A contract account represents a smart contract. Every account has a coin balance. The participant node can send transaction for Ether transfer, or it can send transaction to invoke a smart contract code, or both. Both types of transaction require fees. An account must have sufficient balance to meet the fees needed for the transactions activated. Fees are paid in Wei. Wei is a lower denomination of Ether. 1 Ether is 10 to the power of 18 Weis. A transaction in Ethereum includes the recipient of the message, digital signature of the sender authorizing the transfer, amount of Wei to transfer, an optional data field or payload that contains a message to a contract, start gas, which is a value representing the maximum number of computational steps the transaction is allowed, gas price, a value representing the fee sender is willing to pay for the computations. Let's examine an actual Ethereum transaction at the following address. Elapsed time values may be different than those recorded at the time of this recording. Observe transaction hash, height of the chain, timestamp, from and to accounts, value transferred, gas limit, gas used, transaction receipt, success in this case, and nonce. This particular transaction is invoking a smart contract. Of course, the smart contract execution incurs fees, and the amount available is specified by the various gas fields. Ethereum block structure has a header, transaction, and runner-up block headers. Block details. This is an actual Ethereum block at the height 4446308. You can actually view this particular block at the link given. It shows the height, timestamp, block hash, previous hash, difficulty and total difficulty, size, gas used, gas limit, nonce, and block reward. Summarizing, accounts are basic units of Ethereum protocol, externally owned accounts, and smart contract accounts. An Ethereum transaction includes not only fields for transfer of Ethers, but also messages for invoking smart contract. An Ethereum block contains the usual previous block hash, nonce, transaction details, but also details about gas or fees limits, the state of the smart contracts, and runner-up headers that we'll discuss later. For a simple Ether transfer, the amount to transfer and the target address are specified along with the fees or gas points. The amount and the fees are transferred to their respective accounts. Here we illustrate a transaction of 100 Ether transfer between the senders and receivers accounts. Note that besides this transfer, 21,000 gas points are paid to the miner who added the transaction block to the blockchain. As discussed in a separate lesson, an Ethereum node is a computational system representing a business entity or an individual participant. An Ethereum full node hosts the software needed for transaction initiation, validation, mining, block creation, smart contract execution, and the Ethereum virtual machine, EVM. This figure depicts the deployment of a smart contract and the invocation of a smart contract. Smart contract is designed, developed, compiled, and deployed on the EVM. There can be more than one smart contract in an EVM. When the target address in a transaction is a smart contract, the execution code corresponding to smart contract is activated and executed on the EVM. The input needed for this execution is extracted from the payload field of the transaction. Current state of the smart contract is the values of the variables defined in it. The state of the smart contract may be updated by this execution. Result of this execution is stored in the receipts. A blockchain maintains both the state hash and the receipt hash. We'll elaborate these in a later course on smart contract. All the transactions generated are validated. Transaction validation involves checking the timestamp and the nonce combination to be valid and the availability of sufficient fees for execution. Minor nodes in the network receive, verify, gather, and execute transactions. The invoked smart contract code are executed by all miners. Validated transactions are broadcast and gathered for block creation. The consensus protocol used is a memory-based rather than a CPU-based proof of work. Who pays for all these operations? Validation, verification, and consensus. In the next lesson, we'll explore the incentive model that answers this question. As we learned earlier in Module 1, mining is the process used to secure the network by validating the computations, collecting them to form a block, verifying them, and broadcasting it. Ethereum also uses an incentive-based model for block creation. In this lesson, we'll explore some relevant concept about fee structure and the incentive model. Every action in Ethereum requires crypto fuel or gas. Gas points are used to specify the fees instead of Ether for ease of computation using standard values. Gas points allow for cryptocurrency-independent valuation of the transaction fee and computation fees. Ether as a cryptocurrency varies in value with market swings, but gas points do not vary. Ethereum has specified gas points for each type of operation. Mining process computes gas points required for execution of a transaction. If the fees specified in the gas point in the transaction are not sufficient, it is rejected. This is similar to mailing a letter with insufficient postage. The letter will not be delivered if it had insufficient postage. The gas points needed for execution must be in the account balance for the execution to happen. If there is any amount left over after the execution of a transaction, it is returned to the originating account. So far, we looked at the gas-related items in a transaction. Now let's look at the gas-related items in a block. Gas limit and gas spent. Gas limit is the amount of gas points available for a block to spend. For example, if a block specifies a limit of 1,500,000 units of gas, and a basic Ether transaction fee is 21,000, this particular Ethereum block can fit about 70 plain Ether transactions. If we add smart contract transactions also into this block, that usually requires more gas, and the number of transactions for this block will likely be lower. Gas spent is the actual amount of gas spent at the completion of the block creation. Now, let's look at the mining incentive model. The proof of work puzzle winner, miner, that creates a new block is incentivized with the base fees of 3 ethers and the transaction fees in Ethereum blockchain. The winning miner also gets the fees, gas points, for execution of a smart contract transactions. That there may be other miners who also solve the puzzle besides the winner. These miners who solve the puzzle but didn't win the block are called omers. The blocks created by them are called omer blocks. These are added as omer blocks or side blocks to the main chain. Omar miners also get a small percentage of the total gas points as a consolation and for network security. Summarizing, any transaction in Ethereum, including transfer of ethers, requires fees or gas points to be specified in the transactions. Miners are paid fees for security, validation, execution of smart contract, as well as for creation of blocks. We presented a high-level view of Ethereum blockchain. We'll use Ethereum as the reference blockchain in the next 2 modules and the following 2 courses. Two techniques are predominantly used for securing the chain and for efficient validation and verification: hashing and asymmetric key encryption. These techniques depend on several complex proven algorithms. We'll provide a high-level view of the application of these algorithms and the critical role they play in securing the decentralized chain in the 4 lessons of this module, namely public key cryptography, secure hashing, transaction integrity, and block integrity. We'll begin this module by discussing the concept of asymmetric key encryption. Then we'll define the concept of hashing, followed by the algorithms used for various hashing needs of the blockchain protocol. We then explain the techniques that use these algorithms to manage the integrity of the transactions and the blocks in a blockchain. Learning outcomes of this module are to summarize the working of the public key cryptography, explain simple hashing and Merkle tree hashing, explore the application of hashing and cryptography in protecting the blockchain. Recall that blockchain's decentralized network participants are not necessarily known to each other. Credentials cannot be checked by the conventional means such as verifying who you are with your driver's license. Participants can join and leave the chain as they wish. They operate beyond the boundaries of trust. Given this context, how do you identify the peer participants? How do you authorize and authenticate the transactions? How do you detect forged or faulty transactions? We can do these things by using public key cryptography algorithm that we'll discuss in this lesson. Let's begin by examining simple symmetric key encryption. The same key is used for encryption and decryption, so it is called symmetric key. Example: Caesar encryption is the simplest one where alphabets of a message are shifted by a fixed number, and this number is called the key. In this example, f is a function defined by shift by 3 an alphabet. Consider meet me at the cinema. You shift by 3 the ASCII value of every letter to encrypt it, and your receiver decrypts it using the same 3 as the key. Shift the other way every character to view the original message. 3 is the key in this trivial example. Since the same key is used for encryption and decryption, it is a symmetric key. Note that the key and the encryption and decryption functions are typically much more complex in a real application. Note that symmetric key encryption has issues. Number 1, it is easy to derive the secret key from the encrypted data. And number 2, the key distribution. How do you pass the key to the participant transacting? These issues are further exacerbated in a blockchain decentralized network where participants are unknown to each other. Let's now examine how public key cryptography addresses these issues. Instead of a single secret key, it employs 2 different keys that take care of both the issues of symmetric key encryption. Let lowercase b, uppercase B be the private public key pair for a participant in Buffalo, New York, USA. Let lowercase k and uppercase K be the pair of keys for the participant in Kathmandu, Nepal. Public key is published, private key is kept safe and locked, typically using a passphrase. And the pair works as follows. Encrypting function holds two properties for the key pair. The public key private key pair has the unique quality that when a data is encrypted with the private key, it can be decrypted with the corresponding public key and vice versa. Now let's look at an example. Authenticate the sender and the receiver. We'll examine just one common use of asymmetric key encryption. Let's say a participant in Buffalo wants to transact with a participant in Kathmandu. Instead of sending just a simple message, a participant in Buffalo will send a transaction data encrypted by Buffalo's private key and then encrypted by Kathmandu's public key. Kathmandu will first decrypt the data using its own private key, then use Buffalo's public key to decrypt the signed transaction data. This ensures that only Kathmandu can decrypt and receive the data, and that only Buffalo could have sent the data. A popular implementation of public key, private key is the Rivers-Shamir-Edelman RSA algorithm. Common application of RSA is the passwordless user authentication, for example, for accessing a virtual machine on Amazon Cloud. Though RSA is very commonly used in many applications, blockchains need a more efficient and stronger algorithm. Efficiency is a critical requirement since public key pair is frequently used in many different operations in blockchain protocol. Elliptic curve cryptography, ECC family of algorithms, is used in the Bitcoin as well as in Ethereum blockchain for generating the key pair. Why ECC, not RSA? ECC is stronger than RSA for a given number of bits. Did you know that 256-bit ECC key pair is equivalent in strength to about 3072 bits of RSA key pair? Both Bitcoin and Ethereum use ECC-based algorithms for their encryption needs. Why should we learn about encryption and hashing, you may ask? The private-public key pair is a metaphorical passport to participating and transacting on the blockchain. Similar to how you learn to use a credit card, secure it and protect it, you need to protect the private key for the security of your assets on the blockchain. In this lesson, we learn hashing that plays a critical role in the blockchain process and also in the integrity of the transaction and confidentiality of data. You'll keep hearing the words hash rate, hash power, hash this, hash that frequently in the blockchain world. For these reasons, you ought to have some basic understanding of hashing techniques. The primary goal of this lesson is to provide you with this knowledge. What is hashing? A hash function or hashing transforms and maps an arbitrary length of input data value to a unique fixed length value. Input data can be a document, tree data, or a block data. Even a slight difference in the input data will produce a totally different hash output value. The following are two basic requirements of a hash function. The algorithm chosen for the hash function should be a one-way function, and it should be collision-free or exhibit extremely low probability of collision. The first requirement is to make certain that no one can derive the original items hashed from the hash value. Can you make potatoes out of mashed potatoes? The second requirement is to make sure that the hash value uniquely represents the original items hashed. there should be extremely low probability that two different data sets map onto the same hash value. These requirements are achieved by choosing a strong algorithm such as secure hash and by using appropriately large number of bits in the hash value. Most common hash size now is 256 bits, and the common functions are SHA-3, SHA-256, and Kechek. Hash value space. How good is 256 bits hash? A 256-bit hash value space is indeed very large. 2 to the power of 256 possible combinations of values. That is approximately 10 to the power of 77. That is 10 followed by 77 zeros. Odds of a meteor hitting your house is higher than generating two of the same hash values of 256 bits when applying this algorithm. Great. Let's proceed to explore some techniques now. We'll compare two different approaches for hashing based on how the constituent elements are organized: a simple hash and a Merkle tree hash. Here we illustrate simple hashing and Merkle tree hashing with add as a hash function. We use the data 10, 4, 6, 21, and 19 and add as a hash function. Actual hashing functions are quite complex and are variations of SHA-3, and the data values are much larger, many 256 to 512 bit values. In the simple hash approach, all the data items are linearly arranged and hashed. In a tree-structured approach, the data is at the leaf nodes of the tree. Leaves are pairwise hashed to arrive at the same hash value as a simple hash. When is a tree-structured hash used? When is a simple hash used? When we have a fixed number of items to be hashed, such as the items in a block header, and we are verifying the composite block integrity and not the individual item integrity, we use simple hash. When the number of items differ from block to block, for example, number of transactions, number of states, number of receipts, we use the tree structure for computing the hash. Note that the state is a variable that may be modified by a smart contract execution, and the result of the execution may be returned in a receipt. We learn more about their use in course 2. Tree structure helps the efficiency of repeated operations, such as transaction verification and the state changes from one block to the next. Log n versus n. Summarizing, in Ethereum, hashing functions are used for generating account addresses, digital signatures, transaction hash, state hash, receipt hash, and block header hash. SHA-3, SHA-256, Kechek-256 are some of the algorithms commonly used for hash generation in blockchains. To manage the integrity of a transaction, we need, number 1, secure and unique account address. We need a standard approach to uniquely identify the participants in the decentralized network. Number 2, authorization of the transaction by the sender through digital signing. And number 3, verification that the content of the transaction is not modified. We use a combination of hashing and public key cryptography that we learned in the last 2 lessons to solve these problems. Let's start with the address of the accounts. Addresses of accounts are generated using public key private key pair. Step 1. A 256-bit random number is generated and designated as the private key, kept secure and locked using a passphrase. Step 2. An ECC algorithm is applied to the private key to get a unique public key. This is the private public key pair. Step 3. Then a hashing function is applied to the public key to obtain the account address. The the address is shorter in size, only 20 bytes or 160 bits. Now that we have the account address, let's look at the transaction initiated by this address. A transaction for transferring assets will have to be authorized, it has to be non-repudiable, and unmodifiable. We'll first examine the digital signing process and then apply it to the transaction. Data is hashed and encrypted. This is the digital signature. The receiver gets the original data and the secure hash digitally signed. Receiver can recompute the hash of the original data received and compare it with the received hash to verify the integrity of the document. Now consider the transaction to be that data. Step number 1, find the hash of the data fields of the transaction. Step number 2, encrypt that hash using the private key of the participant originating the transaction, thus digitally signing the transaction to authorize and making the transaction non-repudiable. Step number 3, this hash is added to the transaction. It can be verified by others decrypting it using the public key of the sender of the transaction and recomputing the hash of the transaction. Then compare the computed hash and the hash received as the digital signature. If there is a match, accept the transaction. Otherwise, reject it. Note that for a complete transaction verification, the timestamp, nonce, account balances, and sufficiency of fees are also verified. As we discussed before, some of the main components of the Ethereum block are the header, the transactions, including the transaction hash or the transaction root, and the state variable, the state hash or the state root. Integrity of the block is managed by assuring that the block header contents are not tampered with, the transactions are not tampered with, state transitions are efficiently computed, hashed, and verified. Remember, the blockchain is supposed to be an immutable record. In Ethereum, the block hash is the block of all the elements in the block header, including the transaction root and state root hashes. It is computed by applying a variant of SHA-3 algorithm called Kechek and all the items of the block header. You will see a real example of Bitcoin block hash in the quiz associated with this module. A typical block has about 2,000 transactions in Bitcoin and about 100 transactions in Ethereum. We need an efficient way to detect tampering and validate the transaction efficiently. Hashes of transaction in a block are processed in a tree structure called Merkle tree hash that we discussed in an earlier lesson. Merkle tree hash is also used for computing the state root hash, since only the hash of the chain states from block to block have to be recomputed. It is also used for receipt hash root. Remember the advantage over flat versus tree representation. If any transaction is to be verified, only one path through the tree has to be checked. You don't have to go through the entire set of transactions. Smart contract execution in Ethereum results in state transitions. Every state change requires state root hash recomputation. Instead of computing hash for the entire set of states, only the affected path in the Merkle tree needs to be recomputed. When the state 19 is changed to 20, that results in the path including 31, 41, and the state root hash 64 to be recomputed. Only that path is recomputed, not the entire tree. Now let's move on to block hash computation. Block hash in Ethereum is computed by first computing the state root hash, transaction root hash, and the receipt root hash shown at the bottom of the block header. These roots and all the other items in the header are hashed together with a variable nonce to solve the proof of work puzzle. Block hash serves two important purposes: verification of the integrity of the block and the transactions, formation of the chain link by embedding the previous block hash in the current block header. If any participant node tampers with the block, its hash value changes, resulting in a mismatch of the hash values and rendering the local chain of the node in an invalid state. Any future blocks initiated by the node will be rejected by other miners due to hash mismatch. This enforces the immutability of the chain. Summarizing, a combination of hashing and encryption are used for securing the various elements of the blockchain. Private-public key pair and hashing are important foundational concepts in decentralized networks that operate beyond trust boundaries. In the last module, we learned about the use of public key cryptography and hashing for validation of transactions and blocks. After this module, you will be able to define elements of trust in a blockchain: security, validation, verification, and consensus. Discuss consensus protocol, an algorithmic approach to add a new block and to secure the chain. Explain trust in the robustness of the main chain. Illustrate trust in managing exceptional situations such as hard fork and soft fork. Let us understand trust using a common everyday scenario in a centralized system such as an airport system. Say you want to fly out of the Buffalo airport. The airport authority will have pre-established a secure environment for people to arrive and depart. This establishes the base trust. Then there is additional trust once you enter and your passport and travel documents are verified, validated, and your baggage is screened. Even more trust in you is established when the airline staff checks your boarding pass at the gate and you enter the aircraft to fly. Now let's consider a decentralized system. There is nobody checking your credentials and certifying that you're trustworthy. Then how do you do it? You do it by using algorithms and techniques discussed in the last module. Let's examine how these will help address the trust issues in a blockchain. Similar to our airport scenario, trust in a decentralized blockchain is also about securing, validating, verifying, and making sure resources needed for transaction execution are available. This is accomplished by securing the chain using specific protocols, validating the transaction and blocks for tamper-proofing, verifying the availability of resources for transactions, and executing and confirming the transactions. The trust trail is defined by these operations: validate transaction, verify gas and resources, gather transactions, execute transaction to get a new state, form the block, work towards consensus, finalize the block by the winner, and everyone add the block to their chain and confirm the transactions. We will examine each of these steps. Steps 1 and 2 are validate transaction and check resources. In the case of a Bitcoin, there are about 20 criteria that are to be checked before a transaction is validated, as discussed in Module 1. Similarly, in the case of Ethereum transaction, the syntax, the transaction signature, timestamp, nonce, gas limit, and sender account balance are validated before execution. The fuel or gas points and other resources available for smart contract execution are also validated. Transaction signatures and hash are also verified. Step number 3 is execute transactions. Merkle tree hash of the validated transactions is computed. This is in Ethereum. This is the transaction root of the block header. All miners execute the transaction for Ether transfer, as well as for execution of smart contracts. The state resulting from transaction execution are used in computing the Merkle tree hash of the states, the state root of the block header. The receipt root of the block header is also computed. In the next lesson, we'll continue to talk about the next step in trust trail, the consensus process. A secure chain is a single main chain with a consistent state. Every valid block added to this chain adds to the trust level of the chain. The miners are vying or competing to add their block to the chain. What if everyone wants to add their candidate block to the chain? Each of the candidate blocks is by a competing miner. Which is the next block to be added to the chain? Can they agree on the next block? Is there a method or a protocol to choose the next block? Yes, there is. It is called proof of work. Proof of work uses hashing. Here is one more application of hashing. Do you realize now how versatile hashing is? We will now discuss proof of work as used in Bitcoin and Ethereum. This is from the point of view of the miner. First, compute the hash of the block header elements, that is a fixed value, and a nonce, that is a variable. If hash value is less than 2 power 128 for Bitcoin and less than function of difficulty for Ethereum, the puzzle has been solved. If it has not been solved, repeat the process after changing the nonce value. If the puzzle has been solved, broadcast the winning block that will be verified by other miners. Non-winning miner nodes add the new block to their local copy of the chain and move on to working on the next block. The winner gets an incentive for creating the block. Proof of work is the consensus protocol used by Bitcoin blockchain and also by the current version of Ethereum. The protocol may be the same. The implementations in these two blockchains are different. Many other approaches such as proof of stake, proof of elapsed time have been proposed. This is a hotly debated area among the developers of blockchain, and you can contribute to it.
Something this important needs to be built by all of us for all of us. You can't just have a small group of people of one kind or one kind of person building this. It's too important. Even the internet itself is not as pervasively disruptive and transformative as the internet on blockchain is going to be, because the blockchain or the internet was and is really an ideal system for broadcasting information. That was great. You know, that was Gutenberg's best day, right? But it didn't invent a way of doing transactions without having centralized authorities in there, like banks and others, and you have issues, like we are seeing with Facebook today. Right? There are problems with central authorities being in control of your identity or your information or your transactions. Right? So, but being able to democratize that and spread it all over the world That's powerful, but it's also really powerful, which means it better be built by more than just a few knuckleheads in a building, with only one perspective on things. So it's very important that these technologies are being built in open source, but not just open source, openly governed open source. Meritocracies. There are hundreds of people all over the world building the protocols for Ethereum and Hyperledger and other things. And that's the way it should be. We need more of that, and we need more kinds of people. It needs to be a highly diverse group of people. And what's great about blockchain is that it's so young, there is no group of people who can tell you that you don't know what they know, right? That they're better than you. Anybody that tells you that they know more about this than you do, they might know a little more, but mastery is 13 years and blockchain hasn't been around that long, right? So this is your opportunity. If you're a student who isn't represented by a lot of people that look like you or think like you, this is your shot. You can get in there and you can say, no, I'm the expert. I'm the master on this. And that's good.
Trust is not only about executing regular operations correctly, but also about managing exception satisfactorily. Robustness is the ability to satisfactorily manage exceptional situations. It's all the more important in a decentralized autonomous network, such as a blockchain, where there are no intermediaries minding the store. This lesson is about some of the exceptions that may occur during the blockchaining process. We'll discuss just 2 exceptions in this lesson and more in future courses of the specialization. Have you wondered, what if more than one miner solves the consensus puzzle very close in time to each other? What if more than one transaction references as input the same digital asset? This situation is called double spending. Handling such exception satisfactorily is critical for ensuring the security of the blockchain. We start with a secure chain indicated by 3 blocks, and we want to add to this chain. Here you see 2 miners have solved the consensus puzzle very close to each other. Bitcoin protocol allows this chain split or 2 chains for the next cycle, one led by each of the competing blocks. The probability that the next block will happen at the same time in both these chains is extremely low. So the winner of the next cycle for block creation consolidates one of the chains, and that chain becomes the accepted chain. In this case, the newest block is added to the main chain. Now this chain is the longest and the valid main chain. The transaction in the other blocks are returned to the unconfirmed pool. Summarizing, with a very low probability, the main chain may split. But if it does, the Bitcoin protocol has methods to consolidate it to a single chain within a cycle. Ethereum handles more than one puzzle winner by allowing Omer or runner-up blocks and allocating a small incentive for these runner-up blocks. This incentive model helps in keeping the chain secure. New blocks are added only to the main chain and not to the runner-up chains. The runner-up blocks are maintained for 6 more blocks after they were added. Here you see a blockchain with 2 blocks, one at the height 4, 5, 6, 7, another one at a height 4, 5, 5, 7. The one deeper inside the chain is more trustworthy than the one newly added. Let's now address the double spending problem. There's a possibility that digital currency and other consumables or single-use digital assets can be intentionally or inadvertently reused in transactions. Analogy time. Using our airport flying analogy in lesson 1, this is like an airline double booking a seat on a flight. In this case, a gate crew solves this problem by using ad hoc methods such as asking for volunteers to relinquish their seats for money, etc. In a decentralized network, like a blockchain, there is no intermediary. We need a policy and an automatic, deterministic way to handle this situation. A policy for handling transaction and double spending in Bitcoin is to allow the first transaction that references the digital asset and reject the rest of the transaction that reference the same digital asset. In Ethereum, a combination of account number and a global nonce is used to address the double spending issue. Every time a transaction is initiated by an account, a global nonce is included in the transaction. After that, the nonce is incremented. Timestamp and the nonce in the transaction should be unique and are verified to prevent any double use of a digital asset. Summarizing, well-defined processes for handling exceptions improve trust in the blockchain. There are many other issues such as difficulty adjustment and hard and soft fork exceptions that will be discussed in the next lessons and in other courses that follow. Trust in forks. A fork in the path. Fork, hard fork and soft fork are most common phrases uttered in the context of a blockchain. We hear, at the block 4.7 million, Ethereum did a hard fork. Beware, 2018 is a year of hard fork in Ethereum blockchain. In this lesson, we explain at high level hard and soft forks. Forks are just normal processes in an evolutionary path of the nascent technology enabling a blockchain. If robustness and trust is about managing exceptional situations, hard forks and soft forks are indeed at the front and center. We discussed chain split in the last lesson. That is a minor perturbation in the chain. Such situation is handled as a naturally expected occurrence within the blockchain. On the other hand, occasionally a minor process adjustment has to be carried out, typically by bootstrapping a new software to the already running processes. This is soft fork. For example, the script concept in Bitcoin was introduced using this method. You can think of this as a software patch or a bug fix to address an issue. A hard fork implies a major change in the protocol. For example, the recent change from Ethereum Homestead to Metropolis Byzantine version was a planned hard fork. An important note, after a hard fork, the emerging two chains are incompatible. Please be aware of this. There was an unplanned hard fork in Ethereum protocol, Ethereum Core and Ethereum Classic split, that was enacted to address a critical software issue in a decentralized autonomous organization, DAO, that resulted in a multi-million-dollar heist. We'll discuss this in Course 3, where we study decentralized organizations. Let's discuss the hard fork that happened on October 17, 2017. The Ethereum hard fork was a planned fork. Here are few Ethereum improvement proposals, EIP, for this fork. Parallel processing of transactions. Proof of work consensus still stays, except that every 100 block, proof of stake consensus protocol is applied for evaluating the latter. And minor incentive was reduced from 5 ethers to 3 ethers for block creation. These are just few EIPs. You can look at the documentation for other EIPs. Summarizing, soft fork and hard fork in the blockchain world are like the release of software patches and new versions of operating systems, respectively. Forks are mechanisms that add to the robustness of the blockchain framework. Well-managed forks help build credibility in the blockchain by providing approaches to manage unexpected faults and planned improvements. We are lucky that we have a front row seat to the planned hard fork of Ethereum Homestead to Ethereum Metropolis and watch it as it plays out.